So here's projectile motion. We can think of it as being projected on a coordinate axis, if you like. So instead of, like in tuna, it just had horizontal motion, it's now going to have both horizontal motion and vertical motion. So we're going to project it at some angle, so call it theta, and with some velocity. And it will scribe, as you saw in that little movie, it'll scribe a parabola, the flight path. So that's why, when you looked at his velocity graph, you ended up with a straight line. Because if you differentiate a parabola, you're going to get a linear function. Okay. Incidentally, maximum range, if ever they ask a question about finding maximum range, in our very basic model, because we're not worried about air resistance or anything like that at the moment, that'll always be when the angle is at 45 degrees. So that'll get you maximum range. So one of the first things we need to work out is what's happening initially. This is going to help us build our problem. So the initial conditions, yes, okay, we went off at a velocity at an angle and with an angle of theta, but we want to break it down into, instead of one motion of the parabola, two straight line motions. Because straight line motions are a lot easier to work with and solve problems in a lot of cases. So right, when time equals 0, so when we're starting, I've just drawn up a right angle triangle so I can get, this is a bit like vectors I suppose, that we got our velocity going off at an angle, but I can break that off into a horizontal component and a vertical component. And it's just simple trig to work that out. Now I'm using the dot notation. Remember when we looked at motion, I said in motion for the derivative, sometimes we use the dot notation for derivatives. So x dot horizontal velocity, y dot vertical velocity. And so x dot over v will be cos theta. So the initial horizontal velocity will be v, so its initial velocity times the cosine of whatever angle we're sending it out at. And similarly, using trig for y, in the vertical direction, it'll be v times the sine of the angle. Now, displacement. Depends on our question, but usually we will start at the origin. Sometimes it's convenient to not start at the origin. For instance, if you're projecting from the top of a cliff, you might want to make the vertical displacement the height of the cliff so that the ground is still 0. Otherwise, you could have the top of the cliff being 0, but then ground would be negative, whatever the height of the cliff is. Okay, so remember he said the only thing acting on this is gravity, which is purely a vertical action. So I'm going to start off with that statement. I know the only acceleration that's on this particle is in the vertical direction, and it's g, gravity, and it's going down. So it's a negative acceleration, going in the negative direction. Over in the horizontal, there is no acceleration. Okay? Because once, if you're throwing it, once that ball, or in that case the fireball, once it leaves the trebuchet, you can't influence it anymore. The only thing acting on it is gravity. So there's no force acting on it horizontally once you let it go, because nothing's in contact with it anymore. So to find velocities, it's just like we did in the 2 unit. To go from acceleration to velocity, we integrate. Integrate 0, we'll get some constant. I've called it constant 1 because I'm going to end up with lots of constants in this problem. And over there in velocity, I'll get minus gt plus a constant. Okay, those initial conditions we worked out. So v cos theta and v sin theta, we can sub those in and we'll come up with our constant. So horizontal velocity is v cos theta. That is, of course, a constant amount. Remember, v was the velocity we imparted on it. That's not going to change because once we've let it go, that is its velocity it started with. And that angle theta is a fixed amount as well. So horizontal velocity is a constant, which makes sense because acceleration is 0. If acceleration is 0, its velocity can't change. Vertically, however, it does change. And like we just saw in that little clip, we said velocity is always decreasing because we start with our constant v sine theta, but then we're going to be taking away gravity times time. And so it'll get more negative as we're going along. Okay. Okay, so find displacement. So we integrate again. Remember, v in cos theta is just a constant. So it's like saying integrate a constant. You'll get a constant times t in this case, because we're integrating with respect to t. So I've got vt cos theta plus yet another constant. Over in the y, I get minus a half gt squared plus vt sine theta plus a constant. Now, one of the more common mistakes with these sort of questions is to integrate the cosine or integrate the sine. Remember, in this problem, cosine theta and sine theta are just constant values. So we don't integrate the trig. T is the variable we're working with here. I've set it at 0, 0. So because of that, our constants turn out to be 0. So I end up with x equals vt cos theta and y equals minus half gt squared plus vt sine theta. Effectively, what we've now got are the parametric coordinates of a parabola. Okay? Because that flight path was a parabola, remember? And what we're saying is, instead of looking at the parabola as one shape, we're breaking it up into its x coordinates and its y coordinates. That's one of the things parametrics does. So the parameter is time. So at any time we can find the x coordinate or the y coordinate of our parabola. If we wanted to find the actual equation of the parabola, then just like we did in parametrics, I could eliminate the t, substitute it in. Okay? So t would be x over v cos theta. I'd sub that into y, and I end up with a quadratic equation, although I might tidy that up a bit. Sine on cos could be tan, and cos reciprocal cos squared sec squared. But you can see we get a quadratic equation, basically. That's the equation of the actual flight path. So when we're solving these problems, sometimes it might be easier to work with the parabola. And we've done a lot of work on quadratics, where we're finding roots and things like that. So that might be a useful way of looking at the problem. Other times it's useful to look at it in the parametric form and solve it that way. So we've got two different ideas we can work with in projectile motion. With these 6 equations that I've underlined, although we don't usually use the acceleration ones other than to derive them, we can pretty much solve any equation, or any problem, I should say. So, actually I'll keep going there. Here we go. So, common sort of questions that they like to ask, which I suppose are obvious questions. Things like, when does the particle hit the ground? So you've just got to ask yourself logically, what's happening when it hits the ground? What's something I know for sure when it hits the ground? Well, I know for sure that the y coordinate's going to be 0, if that's where I've set the ground at. If it was that top of the cliff question, I was saying it might be negative something. Okay? Well, in that case, I'm not interested in any other equations. All I need to use is that parametric equation with y, and I can solve that equals 0 and work out what the time was. Problem solved. What's the range of the particle? How far does the particle go? Okay. I can find when it hits the ground, like I did in the first part, but once I know when, I can get that t, that parameter, now substitute it into the x equation, and I'll find out where it hits the ground. I'll get the x coordinate, so then we'll substitute it into x. Of course, if I looked at it as the parabola, where it hits the ground would be the roots of the quadratic, because it's like what's saying the x-intercepts, if that's where I've set it to be 0. What's the greatest height of the particle? So what's happening at the top? What do I know for sure? Well, if something's moving up and then it's moving down, before it moves down, it's got to stop. So at the highest point, that vertical velocity must be 0, because it's going to go up, then it's going to come down. So I can use that equation we worked out for y velocity, vertical velocity, solve that equals 0, and that will tell me the time when it stops. And then to find out how high, I could substitute that now into the y equation, sub that parameter t in, whatever value we got in the first one, and we'll find out where it stops, how high it goes. Of course, if I'm talking about the quadratic, if I've got it as the quadratic, we're talking about the vertex. And so we know it's going to be the y value of the vertex. So I could do minus the discriminant on 4a. what angle does the particle make with the ground? So when it hits, at what angle it's coming in? Now, if you're projecting from the origin, then it's a very easy question because the parabola is a symmetric object. So if I'm projecting from the ground at an angle of, say, 20 degrees, then it must logically land with an angle of 20 degrees. So they're probably not going to ask us that one. That's a little bit easy. It might be where we're not projecting from the ground, we're projecting from higher up, and then what angle does it hit with the ground? But the way we do it is, okay, we've got to find out when it hits the ground, and then we work with the velocities. That will give us the angle it hits the ground. So I'll find out the vertical velocity at that time, and then the horizontal velocity, well, that's always constant, remember? And then I can just draw up a triangle and I can work out the angle that it hits the ground from that with a little bit of trig. Or if I'm working with the parabola, what I'm saying basically is the slope of the tangent at that point, and we know slope is equal to tan theta, so I can do calculus on my parabola to work out the slope of the tangent, and then I can say, oh, okay, well, slope is tan theta, I can now find the angle it hits the ground. So again, depending on whether I'm working at it in a parametric form or whether a Cartesian form, I can come up with that solution. Okay, so what's going to happen? All we know about projectile motion is, remember that one fact, that the only acceleration, the only thing that's acting on this particle, whatever it is we're throwing, is gravity. So of course we can quote that. I mean, that's the basic idea of projectile motion. Usually then we would go and derive everything else. Although lately in the HSC, they've been giving you equations to save time and said, oh, well, look, here's the displacement equation and here's that, and then you don't have to, derive everything. But there is a chance you might have to. So we'd go through the process. It won't always just be V and theta. They might actually have actual values for V and actual values for theta, so you end up with numbers rather than V cos theta and so on. Initial conditions, V cos theta, that's fine too. We can quote that because that's just simply drawing up our triangle and saying, oh, well, resolving the components of velocity. And that's pretty much all. Everything else is derived from that point on. So it's unlike the way you approach it, I guess, in physics. Now, we've taken it from scratch. But unlike physics, we have two ways of approaching it. We can take it from a Cartesian way, or we can look at it from a parametric way to solve our problems. All right, well, so let's do a basic sort of question. Ball's thrown, initial velocity 25 metres per second, angle, well, rather than say the angle, I've just said whatever the inverse tan of 3/4 is to the ground. Determine, there you go, greatest height obtained. So the first thing I'm going to have to do is derive my equations and go from there. So my initial conditions for this one, the angle is the inverse tan of 3/4, so opposite over adjacent. Hypotenuse works out to be 5 then, it's that nice 3, 4, 5 triangle. And that gives me an initial velocity was 25 metres per second, so we get 20 metres per second initial horizontal, but that it'll always be that horizontally, because remember, that's a constant. And vertically, we get 15 metres per second we'll start off with. And so now I'll just go through and derive it. Also, for the sake of this question, a lot of times, rather than using 9.8, they might say, just use 10 for gravity. It just makes the maths nice. If they don't say it, then I'll probably leave it as G, or 9.8 obviously is the other one they often will ask you to use for gravity. So it's just basically going through the same process. Integrating, I get my constants. I've got to work out what my constants are. So when t equals 0, I know initially we had 20 and 15 respectively. Subbing those in, there's my horizontal velocity, there's my equation for vertical velocity, and integrate again. But very easy integrations, you'll notice. They're just polynomials that we're dealing with, and it's going to be the same every single time. And we should end up with a quadratic there. There it is, minus 5t squared plus 15t. Now, I have a choice. I could create the quadratic equation if I prefer to work with the parabola rather than working with parametrics. But it depends on what the question's asking me. So, all right, greatest height occurs when the velocity is equal to 0. So I'll solve velocity equals 0. T is 3 on 2. And now I'll sub that in to find where it is, 45 on 4. So there's my answer. Greatest height is 11.25. This is the one situation where I usually won't write my answer in improper fractions. I think if I'm answering a practical question, it makes more sense to say 11.25 metres. If someone's going to ask you how far is something, you wouldn't say, oh, it's 45 over 4 metres away. You would say, I mean, it's a natural thing to say. Not to say you'd get it wrong if you left it as 45 on 4, but I just feel it's more natural to give the answer as 11.25. Okay, range, how far has it gone? Well, I now know the time of the flight is 3 seconds. We just worked that out. Because this one started from the origin, I'm dealing with a symmetric object. So I know when it reaches its height, the time must be how long? 1.5 seconds, right? Because it's symmetry. If it's taken 3 seconds to hit the ground, then 1.5 seconds till it gets to the middle. Because remember, it's a constant velocity. So it's going to horizontally sweep out the same amount in each time period. So when t equals 3, the range is 60. So that's the quick way of doing it. If you have already worked out that the time of flight is 3 seconds, which I had done in the previous one. So the range turns out to be 60 metres. Now, because this question started at the origin, as I said, it would be a very boring question to simply say what angle does it hit the ground with, because it would be the same as it was projected with. So after half a second, what's it doing? What's going to be its velocity and what direction is it travelling after half a second? So subbing those into the velocities, obviously horizontal stays the same, that's 20. Vertically now, I've got a vertical velocity of 10, so I'm still going up because it's still a positive velocity. Let's draw up my triangle. Remember, if you want to work out the angles, you play with the velocities to work out the angles. So drawing it up, it's 10 up, 20 across. Pythagoras just tells me it's 10 root 5. There's my velocity. And trig will tell me the angle, roughly 26 degrees 34 to the nearest minute. So all right, I know I'm still travelling with a velocity of 10 root 5 and an angle of 26 degrees 34 to the horizontal. We're still going up. What is the Cartesian equation then? Let's actually work it out. So we get our parametrics. So t is x on 20, make t the subject in the x. Substitute it into the y, and there's my quadratic equation of the path. So all right, now that I've got the quadratic, let's actually use that to solve those same questions. So the first one said what was the greatest height. Well, that would be the y value of the vertex. If I've got the equation of the thing, so I can say, okay, the discriminant of that quadratic is 9 on 16. And I know the y value of the vertex will be minus the discriminant on 4a. And there's our answer, 45 on 4, same as before. The range, well, I've got to find the roots, basically. So I'll factorise it. That's probably the easiest way of doing it. I know it starts at 0, so there's my first solution. The other solution is 60 if I solve 3 minus x on 20. So the roots are 0 and 60 of this quadratic. So 60 must be the range because 0 is obviously where I started from. Velocity and the direction. Well, when t equals a half, x was equal to 10. Sub that in. So I still got to use my parametric, I guess, to work out the x value. So I can then go and differentiate, sub in the x value to y dx is equal to a half. And so I can then say, oh, well, tan theta is a half. That gives me 26 degrees 34, same as we got before. And velocity, I can use x over t cos theta. And I've just drawn up a little triangle. It is a very little triangle, isn't it? So I can work out what cos theta is, and I get 10 root 5. So sometimes you might want to play between the two, because you'll notice in C, I still had to use parametrics to get some of the information that I needed to solve that problem, part C there. Okay. So 3G and 3H in our 3-unit Cambridge book is on projectile motion, and we'll spend the next couple of days on that.